process, our learning steps in these chapters is about this. From here, again, let me borrow this one to here. So this is our systems. Okay, this is our input. So for example, here we have an input 2, say with the phase angle, say the omega t. Okay, so that is our input signal. For the system game, that system game depends on the G and phi. So that is, for example, our systems. Say you can see the system basically is a function. For example, G, and let me make one example, is 1s plus 1. Okay, and then for our signal analysis, the frequency domain analysis, we replace J equal to S equal to J omega. Okay, so when we do the analysis, always keep in mind this is your first step, replacing S equal to J omega in a way it can get us into the frequency domain analysis. Okay, so right now it's this one. So right now you can see G equal to magnitude equal to 1 and omega squared plus 1, right? Okay, so for example, when say at omega equal to 0, so no oscillations, the magnitude equal to 1. And let me call the G here, the G equal to 0 degrees minus J omega plus 1 equal to minus arctangent omega. Okay, so that's the phase. So we can try, so say the first scenario when omega equal to 1, then omega equal to 0. Okay, no oscillation, then basically this one equal to phase 0, right? So the output will be equal to 2 and phase is omega t plus 0 degrees. Right? Okay, 0 degrees. When omega equal to 1, then here we're going to change. So maybe, sorry, probably let me write it down here. So when omega equal to 1, then G will become how much? 1 over 2, and then the phase equal to minus arctangent, minus arctangent 1, right? So arctangent 1 equal to how much? Anyone can help contribute calculators for me?
Negative 45.
Huh?
Isn't it 45?
45 degrees?
Negative
Okay.
45?
Negative 45 degrees? Okay, so thank you. So in this way, the output will be equal to 2 times square over 2. So basically that is the 2 divided by square 2, and then this is omega t minus 45 degrees. Right. So here, if we keep changing omega equal to certain numbers, then you can see this will be keep changing. Got it? And this is the system descriptions. The system descriptions is governed by this. And the system's behavior keeps changing when we have a different omega. So, and once we can govern the behavior of the system, then for the output is piece of cake. Because here we simply utilize this rule, multiplication. The magnitude of the output simply is a multiplication of the 2. The phase of the output simply is the addition of the 2. So right now you can see the key issue is governed by the system. The system behavior is different at a different omega. So now we're back to the little bit more detailed of this chapter. The frequency domain analysis is about the analysis of the system behavior at the different frequencies in terms of the system's magnitude and the system's phase. Okay, so that means for this frequency domain analysis, usually we describe the system. By, that is for analysis, okay? By this. The first one, we plot This is the magnitude of the J omega. Let me put into the good way. This is omega, and this is the magnitude of J omega. Okay? So we want to know the magnitude of the G, say when omega equal to say 1.1 and say 10. Usually we put it into the log scale, and most of the time in log scale. Okay, so now we want to know what is the value of the systems. Then this way we have a characteristic curve for the system behavior at the different frequencies. Okay, so the frequency is radian per second. Again, for the phase, that is log, again, usually is in log scale. And we want to know the phase, and that is the phase G, J omega. So now again, for different one, we want to know what is the phase, say 0 degrees, 90 degrees, and say minus 90 degrees, etc. Okay, we want to know the behavior of the systems, the angle. Once we have these curves, then simply you tell me, okay, which frequency you want to work with, then we simply plug in that number, and then we get this one done quickly. Got it? Good? Okay, so the first part of these chapters about the frequency domain analysis is to teach you and how to build up this kind of drawing, which means the plot the magnitude of the system in terms of the log scale of omega, and as well as plot the phase angle of the system in terms of the log scale of omega. And this one, basically, we name it as a Bode plot. Bode plot. That is the first portion. You good? Yes or no? Yes, right? Okay. Then the second one is we're going to have the Nyquist plot. The Nyquist plot simply is to convert this one into the complex plane. So real part and imaginary part. So for example, let me label it. So say this is the omega 1, okay, this is the omega 2. We can pick omega 3, etc., etc. You can pick any, you can take any sampling points as possible. So say for omega 1, and we have the G, J omega, omega 1 is that big, and this is the phase of G, J omega 1. Okay, so once you have omega 1, then you can pick the magnitude and you know the phase. You can map that point onto the complex plane. The Nyquist plot is the complex plane. Okay? Again, you pick another frequency, say omega 2, then you have the magnitude, you have the phase. Are you able to map that point onto here? Yes. Let me assume that is here, corresponding to omega 2. And then you simply trace all the points. Then you simply connect those points onto the complex plane. Then this one is called the Nyquist plot of the system. This is a second description of the system. So basically, in the first portions, I will introduce you in detail how to make the Bode plot and then how to make a Nyquist plot, and that will be to constitute the analysis. And then once we have that one, be familiar with those kind of tools, then based upon the Nyquist plot, we do have a stability theory, and that is the second portion. And then that basically can be standalone topic, and I would depend on how much time we have. I might choose to introduce that one or no. Okay, depends. But my goal is to, based upon the analysis, I want to introduce you the design, control the design based upon those things. And then that will pretty much finish all the semesters. Should be good enough, okay? So how about today we stop here, and then next time